Hello and welcome to this new video. Today we are going to talk about Linux Kernel 6.9. So there is a lot to talk about today, but we're going to answer a few quick questions. We're going to answer, who is Fred? And what is a VDO? And also, will my Freesync screen still work? Coming up. So of course there is no better way to start this new kernel than to read the little note that Linus gave us. So Linus says to us that the Linux 6.9 release, the Linux 6.9 version looks quite stable, so it's good enough to ship. And then he also highlights the work of the Bcachefs team. Now we're not going to talk about Bcachefs today because there's not really any exciting fixes that has been made. Bcachefs, for those who don't know, is a new upcoming file system that seeks to replace file system like ZFS or BTRFS. So it's a good contender. It's fun to see, but we're gonna keep that for another video. That's not really what we want to talk about today because, like I said, there's nothing much interesting in there. Now, we have also more information coming down from Linus saying that he now has a more powerful ARM64 machine. That is really good news because when you compile the Linux kernel, if you have an ARM64 machine or an x86 machine, the way that the Linux kernel is going to be compiled is slightly different, so it's really good that he can test both with performant machine. So that's a good thing. Good news for Linus. Thank you, Linus. We're gonna now be able to check what are the features. So for the features, we're gonna start with everything CPU related. So we're gonna start by answering the first question. Now, what is Intel Fred? Now, I've spoiled it a little bit. Yes, we're not talking about just your good friend Fred. We're talking about Intel Fred, meaning flexible return and event delivery. Now, what is flexible return and event delivery and why does it exist? Now, I'm gonna shorten it to Fred because it's much funnier and because, yes, I'm not saying that another time. So, yes, why does it exist? Now, there's always been a problem with x86 CPU, either Intel or AMD. It's interrupts. Interrupts has always been slow, has always been something that's not really optimized, and also other kinds of events, but interrupts are the one that get the really bad rap. Now, different solutions or patches have been talked about in the different years. For the last 10 years, Intel has pretty much talked about their Fred solution that they were going to implement. And now what we see is that they have fully implemented it in software. Now the problem is that they have no hardware to be able to run it. So that new Fred thing, you're not going to be able to enjoy. But they say that it's simpler and that it leads to simpler and more reliable code in event delivery. And it's probably faster because everybody agrees that interrupts are the more easiest thing to optimize ever because holy Christ was it badly made at the start and everybody knew it. But yes, right now we're just waiting that Intel release actual silicon with the actual for us to actually run the code on it. So it's fun to see that code is out, but yes, we're gonna need to wait a little 3 years to get some CPU Fred action. So yes, that's all for Fred for today. And now we have Intel Fastboot support for pre-Skylake CPUs. Now, pre-Skylake meaning 2015 and earlier. So that's fun to see, but fast boot has always been something that doesn't really change a lot, because the way that fast boot works is that when you boot your machine, normally pretty much everything starts at the same time. So of course your CPU starts, your memory starts, your GPU starts, your USBs start, your disk, HDDs, SSDs, everything starts at the same time. And when you use fast boot, what they're doing is pretty much cutting part of what is starting at the same time as your machine, making the boot process a little bit faster, because they don't have to do some checks, and they don't have to do, well, some starting of the component. The big problem with fast boot is that when it's badly implemented, it gives you a system that is unstable at boot. But with Linux, we're probably never going to see that problem, because, well, Linux code is always written in a way that doesn't really do those kind of issues. So on Linux, what we're going to see is that fast boot pretty much doesn't change a lot of things, because by the time that you can do something on your computer, your CPU will need to pretty much do all the boot process that they would need to do anyway. So yes, that's kind of the thing with fast boot. So good, and at the same time kind of useless. So yes, that's about it. We have Intel Atom that has a new patch for vulnerability. They found a vulnerability in Atom CPU that could expose some values in some data registers. Now, is it a big thing that we need to panic? No, first of all, nobody used Atom CPUs, and it's not all of them that are compromised. And the vulnerability is pretty much, you can guess some of the data if you throw enough things at the wall. So it's not really a big thing. It's good that it's been patched, but hey, we don't really care. We have now on the AMD side of things, AMD comes out with secure nested pages. Now, what are secure nested pages? They are a way to encrypt the memory of a VM so that the hypervisor, the host, cannot see what the VM does. So that's a really fun thing, but that technology already exists. What they added to this technology is that now you have some kind of rule in the CPU that says if you can only read the memory if you wrote it. What it does is that before, because the memory was only encrypted, technically the host could change a big chunk of the memory and now see the result to try to maybe guess the encryption or just mess with the VM a lot. But now, if you do that, the VM will get an error that will tell the VM that, hey, somebody's messing with your memory. So now the VM will be able to know if its memory is being messed with or if it's just normal memory. So that's a very, very good news, because it means that you can have a VM in a completely zero trust environment. So the VM pretty much trusts the hardware and the firmware that's pretty much the hardware at this point in the machine itself, and that's it. That's crazy to me. You can have a VM on a machine that could be 100% infected, and the person would still not have anything on you. They wouldn't be able to get your data. That is crazy to me. We're at that point where if you set up your things correctly. Anyway, that's crazy. And for those who are asking themselves, why would somebody want to do this? Well, it's really useful if you're actually the person hosting those VMs. Because let's say that you're hosting VMs for clients, you really don't want to have access to the client's data, because that's a big liability on you. If you, let's say that your hypervisor, your host, computer gets hacked, well, now you have a problem because your client's data is now compromised. And you're not only looking at some kind of denial of services attack, you're looking at a complete hey, your data is compromised. That's big. That's not something that we want. So that's why those kind of encryption and AMD secure nested pages is that good of an improvement. It's because it makes it so you can, if you set up your server correctly, you can never give the data of your client away. So that's really a good thing. Still continuing on the AMD train, we have AMD P-State support for Zen 2 that has been added. Now, P-State is pretty much the state in which you put your CPU so that you can control its frequency. It's a good thing as always, because you will be able to push the frequency a little bit higher and tell, let's say, the scheduler. Scheduler is the part of the kernel that's able to tell what tasks should run where. You can tell the scheduler, hey, we're going to push that core to the max, and push that really important task to the CPU, to that specific CPU that's running to the max, and all of the other we can shut them down or not push them as intensely. So we can do some optimization there, make for faster computation for less energy. So that's always a good thing. We also have a fun fact. So AMD pushed 20% of the kernel line to the kernel. So when we look at the numbers of line that have been added, they have over 20%. And how did they do it? Well, they pushed lines that weren't really code. So it was a lot of comments and, they have their protocol with their automatically generated line. So that's why they have over 20% of the kernel line. So it's kind of funny to see that 20% of the kernel is pretty much description and definition. Next, we have CPU timer update, which is a fun thing for network, especially because network needs a lot of relies a lot on the timer, but the update on the performance of the timer, of course, benefits the whole operating system because timer is pretty much used everywhere. So that's a good thing to see updated. We also see an update to the kernel's energy model, that we can now update an energy model in real time at runtime. That is really good because it can make it so that we can change the frequency, the voltage, and pretty much everything about the CPU while it's running. And we can make some special calculation with the temperature of the CPU and with pretty much all the information that we have on the CPU to be able to be as efficient as possible. Because, well, some of you may not know, if a CPU is at 20 degrees and if a CPU is at 40 degrees, they're not going to need the same voltage and they're not going to perform as well or as fast within some range of, within some number of megahertz or gigahertz. So it's really good that we can now play actively at runtime with those values. It makes everything fun. Now, we're probably not going to see that much in the desktop space and in the server space. That's probably going to be something more going along with the phone space, because they have a big limit on where they can go with their batteries and their energy. Now to continue, we are entering the FS world. So we have ZoneFS and this file system that I cannot pronounce, huge TLBFS, that now supports ID map mount. So what are ID map mount? ID map mount is pretty much a way to link the user or the group of two mount together. So let's say that you have your computer A that has a user named John, and you have computer B that has a user named John Frederick. Now you will be able to link those two between each other, so that if you plug a drive from computer B into computer A, you can say that John and John Frederick are the same person, thus you can go take on the data without changing the permission on the disk of computer B. So that's a really fun thing that we can now take advantage of with ZoneFS and that other file system. Now that's something that we can already take advantages of in pretty much all of the classic file system, so that's no big news, but it's good enough that we can now have this update. We also see that we removed old NTFS code in, of course it's because we have this new NTFS 3 code that pretty much replaces everything, so it's just standard cleanup. We also see that in NFS v4, admins can now revoke an open or locked file. So that's a good thing, because when well, it's probably not something that happened often if the feature just appeared now, but in any kind of network situation, if you have somebody that locks a file because it's reading it and disconnect for some reason, and the server for some reason wouldn't unlock the file, well then the admin can do it. So it's a good feature. We also have the other thing that I talked about in the intro, the virtual data optimizer, the VDO. Oh yes, what's a VDO? So a VDO is a device mapper that has been added to the kernel. Now this code isn't young, it's something that existed for a long time. It's a technology that has been developed by Permabit starting in 2009. It has been released in 2013. It's been made open source by Red Hat after they bought Permabit in 2017. But what does it do? Well, it provides inline deduplication, compression, zero block elimination, and thin provisioning. Now, what does all this fun thing means? It pretty much means that you can take it, you create a file system, a LVM on your hard drive, you apply the device mapper on your hard drive, and now if you put files on that hard drive, they will be able to be deduplicated. So the way that they do this is that they split your file into small 4 kilobyte chunks, and they compare those 4 kilobyte chunks together, and they do their magic and they make sure that it's not stored 2 times. So they do this, and they do compression after that. So they use, I believe, LZ4 compression algorithms to be able to compress it further, and they have some kind of magic to be able to compress, of course, blocks that would be only zeros, so that too get compressed even further down. Now, that system has been made for big infrastructure. So when they talk about it, they say, oh, you can use it with up to 256 terabyte of storage that can represent a logical size of up to 4 petabytes. Now, we're never going to see that. If you do, please send a video, but I'm never going to use it for that much. I'll probably just have fun and try it on some of my hard drive to see if it's really that crazy, because it really sounds insane when we think about it. That much things done automatically by just throwing your files on that device mapper. That sounds really fun. So that's probably another video that I'll make. So next up, we have more work for the online check and repair for XFS. So that's fun to see that XFS is still getting checks and repaired fixes and patches, because it sounds like it always gets XFS always gets checks and repairs patches at every kernel, so we're kind of wondering when this infernal loop of check and repair will end, but guess what? Work is better than nothing. We also see that ext2, so Extended File System 2, is now deprecated while still being compatible. It's now something that you shouldn't use throughout your Linux system. Of course, it's really old. That should already be something that tells you that you shouldn't use it. But apart from that, it cannot solve the 2K38 problem, the 2038 problem. So that's another reason why you shouldn't use it. Now, like I said, it's still compatible. It's not going to be dropped out of the sky, but they put that deprecated title so that people stop using it. We also have initial support for Fuse pass-through. Now, we have two things to talk about. First of all, we have to talk about Fuse. We have to talk about also about what the hell is the pass-through part of it. So Fuse is pretty much a small little kernel extension and a server. The way that it works is that you normally, when you want to mount a file system, you need to be an admin. There's no way around it. You need to be an admin to mount any kind of file system that is a file system that is purely logical and not hardware based, or that is a file system that is hardware based. You need to actually use admin to do it. Now with Fuse, what it does is that if you have this little Fuse extension in the kernel, you can use the Fuse server to communicate with it and to actually make some file system on the user side, so without administrative privilege. So that's a really good thing that allows for more flexibility on the user side. Now, the pass-through part is because Fuse, because it uses a server architecture, it's actually pretty slow. So when you want to do anything with the file system, you need to first, your application communicates with the Fuse server, and then it communicates with the kernel, and the kernel comes back and to the server, and then it comes back to your app. What they want to do is to cut that down so that you only communicate to the Fuse pass-through inside the kernel. Now, how they do that, that's pretty much a big part of magic that I'm not going to explain because I don't fully understand it, but I find it really good that they're working in that part, because it's fun to see more performance, especially when it gives us more flexibility in user space. So that's all for file system. We're going to move on to other interesting things. We have the minimum version of LLVM that is now upgraded to 13.0.1. So you need a little bit of a higher version of LLVM to be able to compile the kernel. And in the same at the same time, you also need to get the new Rust version, so 1.76.0 instead of 1.74.1 to compile the latest kernel. So there are some actual reason why you cannot compile it with the other version. There are some upgrade that makes the two version incompatible. Now, you can now compile the Linux kernel on a 64-bit ARM CPU. So that's a fun thing, and that's a little wink wink nudge nudge that we can do towards Linus there with his new machine. So the problem that we had before is that you couldn't compile Rust on a 64-bit ARM CPU. So when you would compile the kernel, it would only compile the C++ and the C in the kernel and not the Rust part of it. Now, that's not really an issue because it's only a minor part of the Linux kernel that minor modules that are actually coded in Rust, but it's always good that the kernel is compilable by as much CPU architecture as possible, so good thing that they did it. Now we also have access to GCC named address space, which are pretty much some shortcut names that are reliant on the architecture that you're writing for. I don't fully understand it, but there are special names that point on special things on the hardware. They're faster, I guess. Some people don't like them. I didn't understand fully what they were and what they did, but hey, it's added to the kernel, yay. We also have, that's a fun part of the kernel, we have a cleanup in address space for S390 architecture. Now, throw that on the screen. S390 architecture. That has been discontinued 20 years ago. Last models were made 30 years ago. Think about it. You can run the last kernel, the last Linux Kernel 6.9 on that. That's insane. Anyway, when I talk about cleanup in address space, I just mean that they add some address that were used both for virtual address and physical one, meaning that when you would actually run code on it, if you had an error, there was no real way to know what went wrong. Was it the physical hardware that was telling you that things weren't going well, or was it the kernel itself that was not going well? You couldn't probe that because there was, well, two address at the same place. So now they are cleaning that up. That's not finished, but that's a fun thing to see that there's a rule in kernel kernel devs that if there's still somebody to support an architecture, it's going to be supported until the end of time. And turns out that that architecture that has been discontinued 20 years ago, there's still somebody for it. Well, still gets supported. That's insane. Now we also have basic continuous PTE support that has been added to 64-bit ARM. Now, that's a little bit complicated, and I'm not sure that I completely understand it, but from what I understand, okay, when you look at your memory inside your Linux system, you have pages of memory, which are like those 4 kilobytes pages that are within your memory, and when you call your memory, your CPU does a call and it says, find me that memory at that address, and it will go through all levels of memory to try to find it, and it's a slow process. So to make that faster, they have a translation look-aside buffer, which pretty much tells the CPU, hey, stop looking at all of those crazy places, just look there. It's there. It's gonna be faster. So that translation look-aside buffer, makes everything way faster. Now that already exists in 64-bit ARMs. What they changed is that 64-bit ARMs have this little instruction that says, hey, you don't have to load them by 4 kilobyte chunks. You can load them by bigger chunks if you want, up to 64 bits, I believe, kilobytes, I believe. So the way that it would do that is that in Linux, normally you're not going to have some page that are alone. You're going to have a group of page for one given program. It's going to be called a folio. So that folio is kind of automatically managed by the kernel with the page inside it. So because that folio is continuous, you can use the kernel, the CPU logic, the physical logic on the CPU to actually throw all of that in the translation look aside buffer, so that you can put more in that buffer and have better performance. So that's a good thing. Now, like I said, I'm not sure that I fully understand the technology. That's all very complex, high level things. I don't understand it all, but I applaud all the people that are making the great work to make it true. Now, we have another technology that was added. It's weighted interleaving. Now, what the hell is weighted interleaving? In the kernel, when you have some task, sometimes some task needs to have faster memory. So let's say that you have two tasks. You have one that it doesn't really care, it can be slow memory, and the other one is really mission critical, it needs fast memory. Before, both would be kind of the same, and there would be no way to throw one in a faster memory place, because in the CPU you don't only have DRAM, you also have other kind of memory storage, you also have the cache inside the CPU. But now with weighted interleaving, what it adds is that you can put a weight on that memory. So you can say, hey, I want that one to be faster and I want that one to be slower. So that way you can tell the system, hey, throw that one at the place so it's faster, so it can be used, and make the process faster. So that has been added to the kernel. That's a really nice addition. Following on a nice addition that adds up in performance, we have a patch that allows faster memory management in multi-core application. So the way that they did this is, one of the devs looked at a command, vmalloc, and turns out when you use vmalloc multiple times on multiple core at the same times, it really slows down. The reason why is because vmalloc is to allocate more memory to your program, and you have one big ledger of all the locks of all the memory, and that one place get really locked down when you have everybody call it at the same time. So if you have, let's say, one malloc that runs, let's say that it takes 1 second, just to make the example, one malloc take 1 second. If you add 64 malloc, now each malloc would take 50 seconds. So that was how crazy the slowdown gets. So now the way that they fix this is that they kind of split the memory that was allocated, the memory lock system between each core. That way you add some memory that they didn't have to all look at the same big ledger of lock. They could just look at their own locks and then declare inside their own big pool of memory, you're going there, and they knew that nobody else would be there because that's the memory that's allocated for CPU number 2, and CPU number 3 has a completely different memory pool, so there's no issue there. So that way they could make it really, really faster, so you don't have that issue of everybody doing the same command at the same time, so hey, not working. Now everybody has the same performance because they're not dependent on one another. So that's a fun part. Now to end, we have two last gaming changes. We have third-party Xbox controller now works with Linux Kernel 6.9. How did they do it? Well, expat driver. So now we have the driver inside the kernel for the Xbox, well, the third-party Xbox controller. So that's really fun for those who have it. And now, the last thing that I said in the intro, Freesync is now out of the kernel. Now you may say, wow, does that mean that I won't be able to use my screen anymore? No. You don't have to worry about it. You won't have to throw your screen away. Even if you have a FreeSync screen, it wasn't the kernel that was managing it. The FreeSync extension in the kernel was actually only there for variable refresh rate. Now, the goal of a FreeSync screen normally is to be used with variable refresh rate. For those who don't know, variable refresh rate is pretty much your screen normally has 60 images per second. Variable refresh rate says I'm going to throw those images at the time that the GPU tells me, not at the time that I want to throw them. So it makes for a better experience. So let's say that you had a higher refresh rate screen, a 240 Hz display instead of 60, you could really throw them at the same time as the GPU gives them to you, reduces latency, and makes for a better experience. So that's a fun thing. Anyway, so that's the goal of the FreeSync variable refresh rate, but inside the kernel, it was just a patch put there because of the inefficiencies of all the systems that were over it. So that patch was trying to work with Xorg, with the old Xorg code, with the old compositor put on top of the Xorg code. So all of those old ways of working were kind of working in... If you know Xorg, you know that it was just something that was, let's say that it wasn't really good by the end. Good thing that we went to Wayland, but anyway. So the X way of working wasn't working. So FreeSync was a patch, a band-aid on an open wound. Now they took it out of the kernel because it's not really used anymore. Most people will use actually more modern compositor, or more likely Wayland, which take care of variable refresh rate inside of their system. They already thought about it when they made the system. They were thinking about it, meaning that it takes care of it and it's way more efficient than trying to fit that patch that was actually causing some amount of bugs if it was unable at the same time as the solution, the Wayland and the other compositors on the machine of the people using it. So that's actually a good thing that we see FreeSync getting ripped out of the kernel, because, well, it's actually causing bugs and it's not needed anymore. So yes, that's it. Yes, that's all that was added to the kernel. Now, I'm not going to lie, there are some things that I opted not to talk about, because, I mean, some small optimization about some file system I don't really care, and some small we're adding that hardware from Chinese hardware creator, or I don't care about this. If it was some big hardware, I would find it fun. There was a bunch of optimization in the Intel and AMD space that we didn't talk about, but they weren't really described in much ways. So normally it's because they're minute optimization and things that nobody really cares about. Yes, so it was a really good release. There was a lot of things in it. Now, was it a giant release? No, but it wasn't a small release by all means. So I'm really happy to being able to review it and to be able to review it with you. So I hope that you will stick around. If you've listened to this whole video, I hope that you will that you will subscribe, of course, but also, if you want, please share this video, because if you liked it, well, good chance that other people will enjoy it just like you, and we can actually start something fun and a little ritual where I can make those videos as the kernel comes out, because I understand that I'm at least a week late, but I really want to make those videos as soon as the kernel comes out and give you a little bit more content about everything. I have got some videos in my mind and also some prepared a little bit. I've got the history of Ubuntu that I'm going to release. That's going to be a fun one. There's a lot of things to talk about, but yes, I like speaking, I like making videos, so I hope you stick around to have fun with me. And if you have any question or anything that you understand more than me throughout that kernel review, I hope that you correct me or comment it in the description, the comments. That's the word that I was searching. Okay, I've got nothing to say because I say ha too much. That's all for today. I hope you enjoyed this video and take care.